everybody see my screen?
Yes.
Okay, great. Hello, everyone. Welcome to the UFS webinar. This webinar is hosted by National Weather Service, Office of Science and Technology, the Modeling Division. The goal of these webinar series is to enhance communication and share advancements in all aspects of the UFS in both research and operational settings. My name is Bhavana, and I work with Yang Shui, who is a program manager at OSTI, to coordinate and deliver the webinar. Feel free to contact us if you have any comments and suggestions. Today's webinar is going to be presented by Sarah Griffin, who is a Cooperative Institute member for Meteorological Satellite Studies at University of Wisconsin-Madison. Her talk is going to be about model validation using GO16 brightness temperatures. We will try to finish the presentation by 3:45 and save the last 15 minutes for question and answers. GoToWebinar does not allow the option for attendees to view each other's questions being posted. So feel free to type in the questions during the webinar, and Sarah will be reading them out at the end of the presentation as she answers them. Before we get started, I wanted to quickly show you how to sign up for the webinar notifications. If you go to the UFS portal, which is hosted at ufscommunity.org, and scroll to the Stay Connected section, we have a box here which allows users to subscribe to the webinar announcements. If you click this box, you are taken to a Google form where you can enter your information and you will get future webinar notifications. Also in the Stay Connected section, we have a button to view all the past webinars. You click on this, it takes you to a page which lists all the webinars and the abstracts, and then we have a PDF version of the slides and the YouTube recording of the webinar. With that, I would like to hand over the presentation to Tara, who will be introducing the speaker to us.
Bhavana, Tara, oh, it's unmuted, good. Okay. Oh.
So if we want to, pass the screen over to Sarah, that would be great. But as a course of introduction, I just wanted to say that Sarah has been focused for most of her career on the use of satellite in researching tropical meteorology, as well as numerical weather prediction model evaluation. Personally, I've worked with both she and her colleague Jason Otkin for quite a few years now on the use of the model evaluation tools for evaluation of convection allowing models, such as the HER. She has found new ways to use diagnostic tools, such as the method for object-based diagnostic evaluation and the newly implemented distance map metrics within MET, and uses those to do process studies and diagnostics to better understand why the model is performing well and what is going wrong with the model as well. So her talk today will be focused on both mode and the use of the mean error distance, which is a distance map metric. And so with that, I'm just going to let her get started and tell you all about it. Thanks.
All right, Tara and everyone, thanks for attending. Like everyone said, my title is Model Validation using GO16 brightness temperatures. And there are a lot of co-authors on this presentation, some members from NCAR and the DTC, and then other members from Oklahoma. That's because this is a summation of pretty much 2 projects that we've been working on over the last couple of years. Both of the projects are supported by the Joint Technology Transfer Initiative. Oops, let me click on that. There we go. So just to give you a brief outline, like I said, this presentation is going to be a combination of 2 different approaches. We're going to look at an ensemble-based approach as well as a model configuration-based approach. And what I mean by model configuration is different parameters in the model have changed, and we're trying to figure out what that does to the simulated brightness temperatures. So just for an outline, I'm going to give you some methodology that's used in both approaches. As Tara said, one of the things that we rely on a lot is the method for object-based diagnostic evaluation, or MODE. And I'm also going to just briefly present some of the validation statistics. And then we'll go into our ensemble-based validation and then our model configuration-based validation. So just starting with our methodology, for those of you who are unfamiliar with, MODE is a method to identify objects in forecast and observation fields. So in this image on the left, we have forecast and observation brightness temperatures. And for most of the study, I'm going to be using objects defined by a threshold of 235 Kelvin. So I'm looking for colder than 235 Kelvin, so I'm really looking for those upper level clouds. In our second row, we can see these objects that MODE has identified. They're identified by different colors. If you look in the third row, where it gets a bit more messy, those are the number of objects. So MODE will identify various object attributes for each object. It'll tell you the location of the object, tell you the size of the object, and then it will match forecast and observation cloud objects together. And that's what we see in this kind of vertical table on the right, is MODE has matched forecast object 7 with observation object 17, and says that this has an interest score of 1, which is a perfect interest score. Interest scores describe the goodness of the match. So it's saying it's pretty much, based on the message we assigned, it is a perfect match. MODE will then output attributes for individual objects, like I said, location and size, and also attributes for the match object pairs, such as the distance between the objects, the ratio of the objects' sizes, and other interesting attributes. One thing that is also important that we will use extensively is clusters. And what MODE defines as a cluster is one or more observation object which is matched with one or more forecast object. And I have defined that in order for these matches to be identified as a cluster, they must have an interest score greater than 0.65. This is going to become very useful when we start analyzing matched pairs. So if we look at two examples, we have these gray objects over Nevada. You can kind of tell by the outline that MODE is saying that these are a cluster. If we didn't use clusters, some of it's probably the smaller objects, just because the object ratios would be off, would not have a match. So like the object in the northeast part of, I don't know if you can see my mouse. Hey, cool. If you can see this, like this object probably wouldn't get matched. The green objects over Ontario, Canada are another example. If we don't match these objects, even though they're smaller, it could end up skewing some of our statistics. So whenever we start talking about matching objects and ordering objects, we start with the clusters first, and then we go through and look at any other remaining objects. So as I mentioned, interest scores, that is the similarity between matched, forecast, and observation mode objects. And we have defined interest scores using 4 different object pair attributes. And we've given them certain weights, like the centroid distance is given a weight of 4, and that's the distance between the object's center of mass. We gave a boundary distance a weight of 3, so that means the centroid distance is about 33% more important than the boundary distance. Area ratio, we also gave a weight of 4, and intersection area ratio, we gave a weight of 3. The reasons why some are 4 and some are 3 is that we've noticed that if you have a small object that is encompassed by a large object, you will get artificially high area interest ratio scores, because you would get a probability, or you would get a ratio of 1, or you would have a very small boundary distance, because if it's completely encompassed or even just slightly touching, your boundary distance would be 0, but you would still have a larger centroid distance. So that's why we don't give them as much weight as their corresponding, so centroid distance and area ratio. And then we also include the angle difference and the convex hull difference, even though I'm not going to talk about those attributes at all in the rest of the presentation. So looking at some validation statistics, in both parts of our projects, we have used the mean absolute error and the mean bias error, where F and O are the forecast and observed brightness temperature. So this is a pixel-based or a grid-based metric. And it's pretty much just looping over all the grid points, taking the absolute value of the difference or taking the difference and then averaging. But we're going to do this two different ways. First, we're going to start off over the full domain, which is just what it sounds like. We're going to take every grid point in the domain and compare it to every other grid and compare it to the same grid point in the other domain. So grid point A from the simulation compared to grid point A in the observations, and so on and so forth. Our next method is going to be over individual object or cluster matches. And what we have done here is we have used mode to remove the displacement between the objects. So I have an example image on the right, and we have our GOES observation object and our simulated objects. These objects have been matched by mode. We can see our GOES observation object is outlined here in black. This is actually a cluster, but it also is this little object down here. It's part of the cluster. And then here is our simulation object. So we have defined this rectangle around the objects, and it's defined by the farthest extent of either the observation or the simulated object. So you can see the GOES object here doesn't quite touch the northern boundary. The northern boundary is defined by the simulated object. Simulated object doesn't quite touch the southern boundary because that's defined by the observation object. What we can then do is if we just took this area minus this area, including the brightness temperatures I didn't plot here, this is what our object difference would look like in figure B. But if we overlap them, we get a lot more area where the brightness temperatures are more consistent. And what this allows us to do is it allows us to look at the brightness temperatures of matched objects without having to worry about whether or not there is a displacement between them. We are able to remove displacement. So going on to our ensemble-based validation. This uses a WRF model, and it is 2 5-member ensembles. The first is going to be called the SPP-MP ensemble. And I wish I could explain more about this. This is where my co-authors come in. If you want more information on these ensemble members, there's a paper that's currently in review for Monthly Weather Review describing this. But what the SPP-MP ensemble is it uses time and spatially varying SPP perturbations to the Grappel spectra Y parameter. There's also uncertainty introduced to the cloud water gamma distribution, and the vertical velocity was perturbed. So we just want to see what these changes will do to the cloud features or to the brightness temperatures. And we went and compared this to a control ensemble, which is also 5 members. We have 4 members that are just a white noise perturbation introduced at initialization time to 4 of the ensemble members. And a 5th member is our unperturbed control initialization. So if we look at what these look like, we've looked at 2 different months of data. We have 10 48-hour forecasts from May 2017 and then January 2018. And so in image A, we have on the left our GOES, observed GOES brightness temperatures, and then we have our SPP-MP and control simulated brightness temperatures. If you look at those, you can't see a lot of differences, but there are still some subtle differences. Like if you look over northern Kansas, you can see there's this gap here in the SPP-MP that is not as pronounced in the control ensembles. And then we have the same for January. We have our observed GOES brightness temperatures, and then we compared it to the SPP and the control ensembles. It's important to note that the forecasts are initialized at different times. For May, we're initialized at 12Z, and then January, we initialized at 0Z. So one validation statistic that is just going to be used for this part of the presentation, which is why I'm presenting it now, is called the Continuous Ranked Probability Score. And what the CRPS does is it compares a cumulative distribution function of the simulated ensemble brightness temperatures to the observed brightness temperature at a given grid point. This is why we can't use it in the next part because we don't have an ensemble of brightness temperatures. But here's an example taken from the Wilks Statistics book, where we have 3 different CDFs of ensemble brightness temperature, and our observation brightness temperature is this thick bold line. So the green over here would indicate the CRPS for ensemble 1. This is where, if the observation falls within the CDF of the brightness of the ensemble brightness temperatures. And C and D is what would happen if it occurs outside. So as you can see, much more area is green if the observation falls outside of our ensemble brightness temperatures. We are also then going to calculate the continuous ranked probability score, or CRPSS, which is calculated using the equation 1 minus the ratio of the CRPS for the SPP-MP ensembles and then the control ensembles. And we chose this because we want to see how does the SPP-MP ensembles brightness temperatures change compared to the control ensembles. So if it's positive, that means our CRPS for SPP-NP is smaller than our CRPS for control, and therefore it more closely represents the observed GOES brightness temperatures. So some results using the CRPSS. We actually found out that it was negative for 61% of the forecast hours in May. And one of the reasons for this is the ensemble does not include the observed brightness temperatures in almost over 70% of the May forecast hours and initializations. And this is only a case for about half of the January initializations. So what's happening is that the observed brightness temperature is falling outside of the ensemble range. When we dug into this a little bit more, we realized that that was because May we are usually dealing with smaller clouds. Remember a couple slides ago, we looked at the giant domain area. The January clouds are much more broad, they're much more on the synoptic scale. May is much more on the mesoscale. So therefore, when you're on these cloud edges, it's very easy to not have the observed brightness temperature in the ensemble if you have your cloud misplaced. And we found out that the SPP-MP did produce smaller clouds than the control ensemble, especially in May. The SPP-MP, though, did result in a positive CRPS for 75% of the forecast hours in January. And we can see this in this figure over here. These blues indicate positive continuous rank probability scores, and like I said, that means the CRPS for the SPP-MP is smaller than control, which is what we would like. Up here, there's a lot more of these oranges and greens. We did find out that in January, there is a smaller spread in the ensembles. So that was about in 75% of the May forecast and only 32% of the January forecasts. So looking at some of the validation statistics, the ones that I presented earlier, this is the domain mean absolute error. And what we have found is that between the SPP-MP and control ensembles, there were very little difference in the mean absolute error. This isn't entirely surprising. Again, when I showed you the 6-panel comparing the observations to the ensembles, we could tell there wasn't a lot of difference. There were some very very localized differences, but overall there wasn't a whole lot of difference. So we do have slightly larger differences in January, where the SPP-MP is slightly more accurate. But the differences between the two ensembles are not statistically significant based on a bootstrapping method. We then decided to analyze pixels when the observation or an ensemble brightness temperatures were less than a given threshold. And these thresholds we can see on the bottom. We had the full domain, and then we went to 275 Kelvin, 265 Kelvin, all the way up to 235 Kelvin. And what we found is that in May, the SPP-MP was less accurate for the colder thresholds. And we can see this because our purple line, which represents our coldest brightness temperatures, is much more positive than the full domain. Positive when we do SPP-MP minus control, positive means the SPP-MP is larger. However, it was more accurate for the colder thresholds in January. Most of these are negative except for a couple instances between like forecast hours 26 and 32, where the SPP-MP is not more accurate. we also looked at the domain mean bias error. And we found overall there is a positive bias. Our domain brightness temperatures are too high in the simulated imagery than the observation imagery. But the SPP-MP does slightly lower the brightness temperatures compared to the control. We can see this in our dots over here, way on the right of the image. Our red dot, which is our SPP-MP ensemble, is a little bit less of a warm bias than the control ensemble. And these differences are statistically significant in January. And we can tell us if this cyan teal color does not encompass the 0 line. That indicates that we do have statistically significant difference between the SPP-MP and control ensemble. So why do we have this bias? The positive bias is due to not enough grid points having a brightness temperatures between about 270 and 255 Kelvin. And we can see that here in these top 4 images. These oranges and then even into these reds indicate that there are more GOES pixels that are colder than 270 Kelvin than there are any of our ensemble pixels. For the most part, that meant our ensemble pixels were too warm. So we were missing these like lower level, not optically thick clouds. But if we look in this, the final row, which is the difference between the SPP-MP and control, blue indicates that there are more SPP-MP ensemble pixels. So we are getting more of these lower clouds with the SPP-MP compared to the control. It's also interesting that the control has more grid points with a brightness temperature less than 225 Kelvin. And you can see that up here, especially in these oranges. Some of these get, this is a percent change, so some of these get a bit, just a bit out there, because if you only have a small number of pixels, 1 or 2 pixels can make a big difference. But we can see a consistent layer of these oranges in January and also in May, which indicate that there are more control ensemble pixels at these thresholds than the SPP-MP. And this is good because if we noticed up here, when you're looking at both May and January compared to the observations, we had too many of these pixels. So the SPP-MP is reducing the number of these pixels that are colder than 225 Kelvin. And that is more accurately represents the observations. So moving on to mode, since I was talking about it so much. Like I said, these objects are identified using 235 Kelvin. And we wanted to look at the area encompassed by the simulated objects compared to the observation area. We have May on top, January on the bottom, and we can see that for May, there are simply too much area that are as part of these objects. And again, that's not entirely surprising based on the figure at the, our previous figure. More pixels we would assume would equal more area. But it's surprising just how much different it is in May. January is a bit different. Again, there are more pixels, more grid points that are usually associated with simulated objects compared to the observation objects. It is a bit closer though in January than it is in May. And for both months, the average area encompassed by the SPP is larger than the control. Also looking at the number of objects, the SPP-MP actually had fewer objects compared to the control in January, and we can see that down here. But for the most part, they both produced much fewer objects than in the observations, but we also had more area, so therefore our objects were larger. There's also slightly more cloud objects in the SPP ensemble than the control during May. It's not nearly as noticeable, and it's also much more represents the number of GOES objects compared to January. So like I said, our average object size is smaller for the SPP-MP in about 44% of May forecasts and only 14% of January forecasts. That's because we had areas that were about similar, but much fewer objects in the SPP-MP. So we have larger objects here. So looking at those objects, comparing the mean absolute error, and then we'll look at the mean bias error. When we looked at the full domain, there was very little difference between the SPP and the MP. When we look at just the objects, the mean absolute error is much lower than the control. And this is the case in both months, in May and in January. And some of these differences are statistically significant. This figure is much more noisy because we're dealing with objects instead of the full domain, so it's not nearly as smooth. The bias is also lower compared to the full domain. And in May, we actually have a negative bias. As I mentioned, the SPP objects are usually a bit larger in May than they were in January. However, the brightness temperatures weren't nearly as cold, so we're kind of doing a balancing act of objects that are larger than the control object for SPP MP, but the brightness temperatures aren't as large. So pretty much what ends up is giving us is just a slightly negative average bias. However, when we looked at the full domain, the average bias was positive. So this would be considered an improvement. The January object brightness temperatures are still too high. We still have a positive bias, meaning the brightness temperatures aren't as high compared to the observation object. But even though it kind of overlaps over here, the SPP MP bias is slightly lower. It's slightly less positive. And our bias is highly correlated with area ratio. If we have larger forecast objects compared to the observations, we're going to have a lower bias. That's kind of a given. So what are some conclusions we can draw from this one section of our presentation? Model accuracy, which we define using the mean absolute error, can be analyzed different ways. And again, we're using the same metric. It's both mean absolute error, but they were similar over the full domain. They had lower accuracy when we're using grid points with a brightness temperature lower than a given threshold. And we use grid points with a brightness temperature lower than 235 Kelvin. And we also did objects lower than 235 Kelvin. And so while I had lower accuracy when we looked at grid points less than 235 Kelvin, but better accuracy when we looked at the objects defined with 235 Kelvin, what that means is that we're dealing with a lot of displacement between these clouds in the SPP MP, at least compared to the control. That would be a result of larger displacement. So when we define objects, we remove the displacement, we got a higher accuracy. It also could be because when we look at objects, we are only looking at objects with match object pairs. So if a model did produce, we have 8 objects in the observations, but 18 objects in the simulated imagery, and assuming there are no clusters, we're only looking at the mean absolute error for those 8 objects. So therefore, some of the lower accuracy in May for the threshold greater than 235 Kelvin could be due to additional objects that do not have a match. It is not guaranteed that every object is going to have a match. We try to match as best as we can, but if there's no objects to match to, there's no objects to match to. The bias also differs depending upon the analysis domain. We saw it was positive over the full domain, but it was less positive and even negative for the match object pairs. So it's positive over the full domain. That could be due to, like we saw, the lack of brightness temperatures between 270 and 250, so we're missing a lot of those lower clouds. But when we look at the upper level clouds, the brightness temperatures are more accurate once we remove displacement and once we don't count for any additional objects. And mode allowed us to analyze object numbers and sizes. We know that the SPP MP produces more cloud objects in May compared to the control, but less objects in January. And that both ensembles produce less objects than the observations. However, the total area encompassed by these objects for both ensembles is larger than the observations. So with that, I'm going to move on to our model configuration-based validation after I get a quick drink of water. So a lot of this work And the previous work is work that was published in Monthly Weather Review in 2020. This next section is work that I'm going to present that is currently under review for Monthly Weather Review. So hopefully we will hear back from that soon. So our model configurations. This uses the FV3 LAM model. And like I said, we're calling this configuration based because we're looking at changing different parameters and seeing how it impacts the brightness temperatures. So we have a control ensemble, which uses the Thompson microphysics scheme, the min boundary layer, the GFS surface, and the NOAA land surface model. This is called control not because we think that it's going to be the best model, but because it is something that we can compare every other model to, because every other model only has one or two things that are different than the control. So we have the MP and SSL model, which is the same as the control model, but we're using the National Severe Storms Laboratory microphysics schemes instead of the Thompson microphysics schemes. Our MP-MG model uses the Morrison-Gettleman microphysics schemes compared to the Thompson microphysics scheme. So all of these names try to correlate to what the difference is between the control. Like our PBL-SH, it uses the same stuff as the control, except for the planetary boundary layer scheme is now the Shin-Hong PBL. PBL-EDMF uses the EDMF, and I'm sorry I don't remember what that stands for right now. I'm guessing it was way too long to put in my little box. But that is the one thing that is different. So when we compare these two configurations to the control, we can see what happens if you change the PBL scheme. And then finally, we have two models that the first one changes the land surface model from the NOAA to the RUC. And then the second one keeps that change, but also changes the surface layer from the GFS to the min. And in this image on the right, you can see an example of all 7 of these configurations. Control at the top, and then our microphysics changes, PBL changes, and land surface changes. One thing that is very obvious, especially if you look at these microphysics changes, is that they do make a big difference when you change them. So here's our control. Look at the Morrison-Gettleman scheme. There are a lot more clouds over the Arklatex region, Oklahoma, not Arizona, Arkansas, Louisiana, Texas. This is in stark contrast also to the NSSL scheme, which has a lot fewer objects. PBL does also matter. We have a much larger flare-up and much colder brightness temperatures over the Kentucky, Tennessee area compared to the control. And also we do see changes with the land surface models. So a lot of this presentation is going to be not only comparing to the observations, but also comparing the models to the control to see what these parameter changes and how these parameter changes impact the simulated brightness temperatures. So a couple methodologies that is just going to be used for this analysis. We are going to use, the first one is called the object-based threat score. And what the object-based threat score is we order the objects from highest interest score to lowest interest score. And we compare the interest score and the area of objects to the total area of objects. So here we're averaging over the area of all forecasted and observation objects. Doesn't matter if they're matched or not. Looping through the number of match object pairs. And so IP is our interest score, and our interest score is then weighted by the size of the matched observation and forecast object. We are also going to look at the mean error distance. What the mean error distance does is it's slightly different than the centroid distance from mode, because it calculates the distance between every grid point identified as a forecast or observation object to the closest grid point identified as an observation or forecast object. And this was done using the distance maps tool in mode. excuse me, yeah, in MET, I suppose. It's not technically in mode, it's in MET. It's in GridStat in MET. So we can see how this calculation is done in the image on the right. Again, our teal objects, if you haven't figured out, apparently I really like teal. It's one of my favorite colors. These are our mode objects. And then in the second row is the distance maps. So this is the distance map from an observation object actually to the nearest observation or observation. Yeah. Let me start that over. This is the distance map from an observation grid point to an observation object. And here we have, I did with the control configuration, the same thing over here from the control grid point to a control object. And then you take the difference. And here we see the difference between the two, the observation and control configuration distance maps. And then finally, we just take the difference and only do it where there are objects. Now you can see our objects that were teal up here are now color coded by distance. And we can also see if like one of the places to highlight is over Mississippi, where we had a control distance map of very little, but we had a much higher distance map for the observation object. So therefore, this is a distance map difference of 175 grid points, whereas a lot of these purples are between like the 0 and the 1, or 0 and 25. And then you can average all of this. So here our mean error distance is about 11 grid points, and here it is 24 grid points. And it's important to note that the mean error distance from a forecast to an observation is not equal to the mean error distance from the observation to the forecast. So going through some results, here's our object-based threat score. The control has the highest average excuse me, I used to do work with overshooting tops. That's why every time I see OTS, I also want to see overshooting tops. It has the highest average OTS, and our MPMG configuration has the lowest. It was also interesting that when we changed the land surface model to the RUC and then the surface to the min, we had our steepest decline in OTS by forecast hour. And this is correlated with an increased number of objects that were identified. Looking at our differences, our parameter changes had a neutral to almost a positive difference early in the forecast hours, as indicated by these like oranges into reds. Configuration minus control is positive. However, as we get into later objects, we start getting into where the control is, where our configuration is higher than the control. So, trying to figure out, why is this? Why does the MPMG have a much lower forecast or a much lower OTS? We broke the OTS into pretty much 3 parameters. This isn't exactly how you would break down isn't the exact way to break down the OTS, but it still gives us a rough idea. There is a similar percent of observation objects that are matched among all the configurations. But if we look at our percent forecast area matched, we can see the MPMG has a much lower percent of area forecast match, and that's because it has the highest number of objects and highest area. We can also look at the average interest scores between our matched objects. And we can see that we have this nice little local maximum around like forecast hour 24 and forecast hour 48. And one of the questions is, why is that? So these are correlated to, these are forecasts initialized at 0Z. So we're looking at, late afternoon, early evening forecasts. So like we said, we have a Diurnal cycle in the average interest scores, corresponding to about 5 to 9 central daylight time. So let me break down our interest scores into their components. So here we have our centroid distance interest score, our boundary distance interest score, our area ratio interest score, and our intersection area ratio interest score. And we can see that this Diurnal cycle is very prevalent in both the centroid distance and the boundary distance interest scores. it's a bit higher than the surrounding interscore. So what this means is that during these times, the objects are closer together than they are at other times during the forecast. If we remove these two attributes, the diurnal cycle in the average interscores is much weaker. So also looking at the area of interscores, like I mentioned, we did the same thing as we did in the previous section, only we also decided to look at a Taylor diagram as well. And we calculated a Taylor diagram using the median of all of these forecast hours and configurations. So for those of you unfamiliar with the Taylor diagram, the solid lines are the correlation coefficient. These dashed lines are the standard deviation. And here we have our observations, or our observed standard deviation is about 150 kilometers squared. And then these semicircles are the root mean squared difference. And pretty much what the root mean squared difference is, it's a mean squared error, but we are accounting for the bias. So if we can see up here, a lot of these models have more area that is encompassed by objects in the observation. If we account for the fact that there is more area encompassed by the observations in the forecast and like normalize those out, the root mean squared difference is the difference between the observations and the normalized area, normalized configuration area. So we do have a diurnal cycle, like we saw in the OTS. But it's important to note that the higher OTS does not correspond to more overlapping area. We analyzed both the equitable threat skill score and the CSI, which I'm now blanking right now on what that actually stands for, but neither of them, we actually had local minimums during this time, which indicate that we're not getting in higher OTS because we just simply have more overlapping area. The Morrison-Gettleman microphysics has the largest area encompassed by objects. It also has the largest spread in the median area, which we can see based on the standard deviation. Changes to the PBL result in less correlation between median area and our teal and our purple here. Pretty much what that means is that it doesn't quite follow the diurnal cycle as closely as the other configurations. Doesn't quite follow the diurnal cycle in the observation objects as closely as it does to the other configurations. And our LSM-RUC surface GFS model has the lowest root mean squared difference. So looking at our mean error distance, the mean error distance from our forecast to the observation is greater than the mean error distance from the observation to the forecast. And this is due in most part to the fact that there are more forecast object grid points than the observation grid points. Again, the Morrison-Gettleman scheme has the highest mean error difference. And it's very obvious, you can see that in this figure A. Again, we also see a diurnal cycle where actually we have a mean error distance that is lowest here, around where we had a highest OTS. Again, we don't think this is indicated by more overlapping grid points based on the comparison between the mean error distance and the ETS, and CSI is critical success index. So based on a comparison to that, we don't think it's related to just simply more overlapping grid points. So our object-based mean absolute error and mean bias error. Here is the mean absolute error, and there's a diurnal cycle in model accuracy. Interestingly, though, it is opposite of the OTS and the mean error distance. Our mean absolute error is highest when our OTS is the lowest. And that's because when we broke down the interscores, we saw that a lot of the average interscores in the OTS were driven by the centroid distance and the boundary distance. That's where our diurnal cycle came from. We removed that when looking at the mean absolute error, which is why we can see these higher mean absolute errors when we're expecting a lower OTS. And so what's interesting here is that both of these are measures of model accuracy. It's just what type of accuracy are you analyzing? So our MPMG has the highest mean absolute error, and our control is the lowest. And the difference is statistically significant. Also, the microphysics with the NSSL scheme has the next highest mean absolute error. If we look at the mean bias error, changing our microphysics schemes has the largest impact. We reduce the bias in the brightness temperatures, or the MPMG has a low bias, so therefore the brightness temperatures are too cold compared to the observations. The NSSL scheme actually has a high bias, so therefore they are too warm compared to the object brightness temperatures. And this is correlated with an increasing number of forecast object grid points compared to the observation objects. So that leads to the question of what happens if we account for the bias. And I know I'm running out of time, but this should be fairly quick. We chose a threshold of 235 Kelvin, which corresponded to the 6.5 percentile of observation brightness temperatures. So instead of defining everything with 235 Kelvin, we can define the objects in each different configuration by the threshold, that is by their 6.5 percentile of brightness temperatures, which you can see over here on the right. They are all colder than the observations. I know we said earlier that the mean absolute error for NSSL was actually still positive, but that was just for objects. This is for full domain because we want to define over the full domain. But what does that do? Honestly, nothing. For the OTS, we still have neutral changes, and the MPMG is still the lowest. If we look at our mean error distance, the mean error distance from the forecast observation decreases, and that's because our object sizes are smaller, so there's going to be a greater distance between the closest objects. There's also fewer objects that are farther away from the observation objects. Excuse me, fewer grid points that are farther away from the observation objects. And when we look at the mean error distance from the observation to the forecast, it increases because our forecast objects are smaller, and MPMG is still the highest. Same thing when we looked at the mean absolute error, mean bias error. Our MPMG has the highest mean absolute error, lowest mean bias error. The NSSL follows the same thing. It is the second highest mean absolute error, and then it's also the highest and it's the only positive mean bias error. So finally, some conclusions is we can change the microphysics scheme from the Thompson, and we do get a lot of changes in brightness temperatures. As I mentioned, Morris and Gettleman results in lower brightness temperatures, and NSSL results in higher brightness temperatures. Both of these are less accurate than using the Thompson scheme. Changing the PBL scheme from the min does have some benefits. It does reduce the high brightness temperature bias, even though they are less accurate based on the OTS and mean absolute error. And accounting for the model bias when calculating OTS and a bunch of the other statistics actually doesn't impact the relative performance of each configuration. So just some future work. All of this was done with the 10.3 micron brightness temperatures. So we want to expand to the water vapor brightness temperatures. Here's a quick example on the side using the 6.2, 6.9, and 7.3 wavelengths. All we calculated was mean absolute error so far. We want to see why are we getting pretty much what we're getting. We also want to know if we can, or see if we can correlate features in the water vapor brightness temperatures to synoptic features. Now we look at these, you can tell in a water vapor feature that, we're expecting an upper level trough here, which is what we see. Can we somehow correlate these? And finally, we want to look at other model fields such as radar reflectivity and snow cover. So with that, I will take any questions. I don't see any questions.
Yeah. If anyone have questions, can you please type it in the questions box, in the chat box? It's a little quiet today.
Bhavana, I think for folks there seems strange. I cannot type in any questions in this box, question box today. Maybe can we unmute everybody?
Let me try that. I can't unmute everyone, but if you can raise your hand, I can mute that person, unmute that person. Okay.
So I'm moving. It's strange today. I cannot unmute folks.
Actually, almost all participants have self-muted, which means you can't unmute. If you can raise your hands, we can maybe unmute that person.
I think the question box is not working. I cannot type any questions.
The chat box is working if anyone wanted to use that.
Yeah, the chat box is working. Folks, if you have any questions, can you type in your question in the chat box? For some reason, the question box is not working. Sorry about this. I cannot unmute Tara even. I don't know what's going on. Can you unmute the Tara, Bhavana?
Tara is self-muted, so we can't unmute her.
Oh, I think it's unmuted.
Yeah.
Okay, yeah.
Yeah, so this is Tara, and I guess being we aren't seeing any questions popping up, maybe Sarah did such a great job of presenting that everything is as a bell to everybody, and so there aren't any questions. But I personally thank you very much, Sarah, for your presentation. I thought it was fantastic.
Yeah, thanks for having me.
I have a question, Sarah. You have shown this a score. So it's a basic on like a few rounds. Do you think the results might change if you do more cases, like do different cases? How many sample size do you think you need to get a conclusion about the different physics package, the microphysics and the planetary boundary layer physics?
Well, we would definitely like to do, I didn't mention, but all of these cases were from May 2019. This was stuff that was run during the hazardous weather test bed. So we would like to do something where we look at, especially a winter case. I don't want to keep using May and July since I did in the last, in the first part of the presentation, but no, May is a convective season and, May and January is more of a winter season. So it'd be interesting to see what the microphysics do during the winter season.
Are those packages already in the MATPLAS already or not?
Which package?
the method you used here, are those code already implemented into MATPLAS already? So
No. The object-based threat score is not in MetPlus. This was something that was developed back in 2013.
Oh, I see.
So it uses the
So-
area from MetPlus, it uses the interest score from MetPlus, but it is not actually in MetPlus.
Do you think this is going to be can be used to diagnose the dinocyclone errors in the UFS?
Potentially. You know, I found it interesting that, like I said, the OTS actually showed that it was more accurate. We were expecting it to be less accurate. So I'm not sure if that would almost give confusing results. This is why I like using mode, because not only does it give you the interest score, but since I explicitly state how I want the interest score for each attribute to be calculated, I can do the breakdown like we saw here. All of these individual interest scores are also not in mode.
Yeah. All right. I guess those probably will be useful for folks to apply into the new version of like GFS 16 if they can use the method to diagnose the dinocyclone in certain region. If that's useful, that would be great. I hope other people can talk. No questions? All right.
Okay, with that, I guess we can call it a wrap. Thank you, Sarah, for making this presentation. All right. Bye-bye, everyone.